Yeah. Yeah. Yeah, so thank you, Clemens. I have the topic of gravitationally driven entanglement dynamics, photon pairs and quantum memories. The talk is aligned with an article we recently submitted and previously published on the archive. It's of course my very pleasure to present the results here towards the RQI community. There are very many very interesting and influential contributions which arose out of these circles. So I'm glad that you lent me your attention. The work I want to speak about addresses research interests of the RQI society in both quantum technological aspects and also regarding fundamental questions of physics at the interface of gravity and quantum mechanics. The work developed over time into a collaboration between us at ZARM and experimenters from the Humboldt University of Berlin, Mustafa Gündogan and Markus Krutzig. And I want to dedicate a special thanks towards my valued colleague Dennis Rätzel, who is also in the audience. Apart from being involved in the whole design of the work, in its whole entirety, he moreover also brought us together with the quantum memory experts from Berlin. And to put it into a nutshell, what we did is basically that we proposed a terrestrial quantum memory-assisted Hong-Ou-Mandel interference experiment operated with frequency-entangled photons in our home-owned drop tower. And why this is reasonable and why this is interesting, I want to point out in this talk. Maybe first I should position the work into the research context of RQI and also my research interest that is centered all around the foundations of quantum mechanics, coherence and quantum entanglement in all its manifold facilities. We are certainly situated somewhere at the fundamental test regime where we consider background gravity, so relativistic effects of an external gravitational field on quantum resources. We also have some intersection with quantum technological aspects because we employ quantum memories in our proposal. To the best of our knowledge, we consider as for the first time these devices in a relativistic context, and they are really important because they are considered as being the key technology for quantum repeaters, which by themselves are considered as being the key technology for a long-distance intercontinental quantum key distribution and communication, quantum communication in general. Certainly these topics are adjacent to various other fields which are of interest for RQI. I want to show you something which I think is, for me personally, very interesting, namely the mathematical aspect. I'm really concerned and interested in the, so to say, mathematical characterization of quantum entanglement. And I think that this could provide some hints of how to concile our most fundamental and successful theories or to get closer to this goal with each other. From a mathematical perspective, certainly the biggest discrepancy between these two theories is that the one is linear and the other is non-linear. So in quantum mechanics, the problems from a mathematical point of view are usually optimization, extremization problems of such functionals, which find the solution as being the solution of a linear eigenvalue problem. However, it is somehow interesting that if one restricts the allowed space of solutions to tensor product states, so separable states, then the story looks very different. These are so-called separability eigenvalue equations, were introduced, I think, before, but really used by Werner Vogel, 2009. These are basically non-linear, is a non-linear tensorial eigenvalue problem of order 3-1. So you feed the solution vector 3 times, so to say, in the operator of interest. Could be the density matrix. You insert the density matrix in order to identify the presence of entanglement, but you can also require the dynamical evolution of some system by these eigenvalue equations which contain the Hamiltonian. And this addresses really the separability problem in its whole generality. What the solution looks like is that you do not find as the solutions, so to say, the extremizing points of the hyperellipse given by the ordinary linear eigenvalue problem, but you find solutions in a Lamé hypersurface. It's also called superellipse, and this makes your solution set very nonlinear. It's somehow interesting that the Ricci tensor can be also considered as a tensor, as a 3-1 tensor, in which you basically feed the derivatives and derivatives of the inverse metric and the metric itself to provide in the end a result that is proportional to the metric itself and the Ricci scalar. In vacuum it's 0, okay, but I wanted to simply show you this, because here the procedure how to get from the very, very complicated separability eigenvalue problem to the simple one is very straightforward. Maybe one can achieve in these Einstein field equations something similar. Indeed, these tensorial eigenvalue problems are very hard to solve. To be precise, NP hard to solve. You need usually luck if you want to scale up the solution. Okay, however, how was the work about which I originally wanted to speak about created? Certainly it was inspired by various articles which arose in the past decade, all the more around the academic descendants of Anton Zeilinger. And what they did is basically they posed quite easy questions to the behavior of a quantum system in the vicinity of gravity and relativistic effects, and received remarkable results in some sense, also addressing these previously criticized and still vividly and controversially debated topics, such as this decoherence issue and why it happens so consequently, despite, as Klaus previously said, there is no a priori a fundamental length scale in quantum mechanics which restricts its applicability to the microscopic regime where it's usually observed exclusively. Yeah, and what they did is basically they considered the behavior of so-called clock states, coherent superpositions of energy eigenstates, owning their name due to the fact that time evolution they precess like a clock around the equator of the associated Bloch spheres. It is very well known and experimentally well confirmed by Haveli-Kiesing experiment and similar follow-up experiments that out of the perspective of a common reference frame, the behavior of such a clock state, in this case here implemented in form of an atomic clock, so hyperfine structure states can be these energy eigenstates, behave very differently depending on where the quantum clock is situated. And what the authors of these articles then basically did, broken down to a simple level, is they considered such a spatial coherent superposition of these clock states. And one central question is certainly that, whether gravity acts on these states in a coherent way, because this would provide us information of how and to which extent gravity underlies and follows the laws of quantum mechanics. And if it did so, what would happen is that the internal, so the energetic degree of freedom, would get, and this was also mentioned several times today already, would get somehow entangled with its motional, with its external, or in this case, positional degrees of freedom, such that this state could not be any more written as a tensor product, and with a particular consequence that somewhere at the time evolution of such a state, it would be expected that the residual state, the residual spatial substate of such a pure quantum state would reside in a decoherent one, in a more mixed one. And how would this manifest in experimental data? The experiment of choice is the Mach-Zehnder interference experiment, here shown for matter wave interferometers implementing these clock states. I want to contrast this experiment with its optical analog of a light interferometer, where the same effect is expected. Certainly in case of photons, if we operate these interference experiments with photons, we cannot anymore speak about measurement of time or that time dilation is really the origin of this effect as it is considered in the matter wave case. Here, however, also in the light interferometric case, the interpretation in the sense that the internal and external degrees of freedom get entangled with each other, also holds true for the single and also for the in multiparticle scenarios. First of all, I wanted to say that the closest analog of some two-level state, it's certainly something like a B-colored single photon, so a spectral coherent superposition of two frequencies. Ramelow showed that they can be generated. However, what both these experiments are expected to reveal in some sense, there are subtle requirements on the synchronization, which I speak about in a second. However, what is crucial is that through the fact that it is expected that the final beam splitter is entered by a completely decoherent spatial substate, and the detectors of such an experiment are only sensitive against, so to say, the spatial degree of freedom. What would be expected is that the visibility, the interferometric contrast, the measure of spatial coherence in Mach-Zehnder interference would drop. However, as I said, the synchronization requirements are very different. In the matter wave case, it needed to be their durations and the distinct arms or the delays need to be equivalent, so synchronized with respect to a common reference frame, where it is the case in optical analog that this drop of the visibility would happen for locally equivalent delays, and vice versa, no effect would respectively occur. And the reason, therefore, is that apart from comparably negligible contributions, these clock states, for instance, atomic clocks, good clocks, standard clocks, if one wants so, should locally always look the same. And in order to change the detection statistics to generate such an interferogram, when the resources look locally distinctly, locally the durations must look distinctly if the resources look the same. When we consider the photons, they, due to the gravitational redshift, they change their character, and this is why this effect happens in this case when we process the photons locally, which is quite an important information for quantum technological applications. In communication, it's much more likely that some of these tasks would be realized with photons because they are better to handle. And there we can recognize the necessity of synchronization. You cannot simply process your photons always locally without running into these decoherence issues or at least dephasing issues, which can constitute some problems. So that we have seen that gravity seems to be somehow capable of altering the entanglement in the single particle in distinct degrees of freedoms of a single particle. In a non-trivial way, it's only natural to ask what happens to entanglement correlations shared between distinct particles, possibly distant to each other. And so are they affected by these gravitational effects? And the answer to this question is yes and no. There are entanglement correlations which are sensitive against these gravitational effects, where others turn out to be resilient. And I will show you these different states. First of all, the most straightforward analog of a single B-colored photon into for a two-particle, in a two-particle scenario where the particles are entangled with each other, is certainly a frequency-entangled photon pair. These frequency-entangled photons are no science fiction, but they were already in the early days of Hong-Ou-Mandel interference in the late 80s investigated by Hong-Ou and Mandel themselves. And meanwhile, they can be generated by various working groups all over the world routinely. One of them is the one of Marco Torres from Glasgow. He operates very successfully rotating table experiments where he basically tests the non-inertial analog of our gravitational considerations and achieves remarkably high redshifts in the order of 10 to the minus 8, 6 orders of magnitude higher than the 150 meters of our drop tower achieve. We describe all of that in a second quantization formalism, for which we also developed entanglement analysis. However, I will further stay in this first quantization notion because it's simpler to follow and it's completely analogous. So we compute for in this formalism both the Mach-Zehnder interferogram, where we recover this well-known visibility, where somehow the redshift enters, and the effect of desire, the drop of the interferometric contrast, we can compute when it happens. It's related to the redshift and the frequency separation between the two spectral peaks of the single photon. We do the same for the Hom case and recover results which are interesting and similar to what happens in the Mach-Zehnder case. We consider the figure of merit in Hong-Ou-Mandel interference, the photon bunching, the difference between the photon bunching and the photon anti-bunching probability. And what we recover here is that we also see here a build-up of or generation of internal-external entanglement. So the two photons get respectively entangled in the internal and external degrees of freedom, and this comes at the cost of lowering the mutual entanglement among the photons, which we respectively quantify with a linear entropy and the negativity. And this is some consequence of entanglement monogamy, because if we consider initially spectrally maximally entangled photons, any other entanglement this spectral state can enter or generate is must come at the cost of lowering the entanglement among these two degrees of freedom, so the spectral degree of freedom of one photon and the other. Furthermore, it turns out that the interferogram, what can be already assumed intuitively as a measure of entanglement, of spatial entanglement of these photons in this experiment, really turns out in a precise mathematical calculation to be a proper measure of entanglement, and it's the negativity, the positivity of the negativity in this case is even sufficient, not only a necessary criterion for the presence of spatial entanglement, spatial correlation, spatial coherent correlation between the photons. It's somehow interesting that the effect of desire, so the mutual spatial decorrelation of the photons, in this case, happens twice as fast as in the Mach-Zehnder case when the visibility drops. And this is the signature of quantum enhanced phase estimation. So if you have more particles, then entanglement can force these particles to collectively react in a more sensitive way. However, this quantum enhanced phase estimation happens here in a very unusual way. Typically, it is recovered for noon states, so states that are aligned. They co-propagate in their spatial degree of freedom, where the just investigated state that shows up in anti-alignment. So each photon propagates in its own arm. Here we recovered quantum enhanced dephasing. I wanted to write. And however, if we consider the noon analog, where the particles, the frequency entangled particles propagate through the interferometer along a same path, then it turns out that these states are resilient against this dephasing effect. However, there's no communication benefit because you cannot distribute co-propagating particles to distinct parties. And then there are still the other 34 out of this all in all 64 states which show up an aligned character in the spectral degree of freedom. This violates energy conservation in the sense that both photons are either in the lower or in the higher energetic state. That means that you at least need more photons to generate these states. The one is again, resilient. The other is sensitive against these gravitational effects. And the one is in particular interesting because, it is for quantum communication because it's resilient against these dephasing effects. However, it is at least an increased energy consumption. Okay, let's return back to the main results. For the parameters of the drop tower, unfortunately, it turns out that the needed interrogation time is 1 second. And you cannot do this with fiberglass cables. You would need 200,000 kilometers, 5 times around the Earth. And instead of that, we use then quantum memories to store the photonic information in material systems coherently. This is based on the phenomenon of electromagnetic transparency and with a control laser which compensates according to a local resonance condition the redshift. One can release and also store the photonic information coherently for amazingly long durations. About hours were already reported. We model these memories with a simple mode swapper operator model where we contain this photonic creation and annihilation operators and the spin wave ones. And it turns out that these rare earth ion doped quantum memories are particularly suited for our purposes. And this is the final result plot for the needed storage time in order to observe the effect of desire in dependence of the frequency separation for various redshifts. Here are the space-based implementations compromising the employment of satellites and so on. Of course, lower interferometric stability. And here we got the terrestrial experiments with a low redshift of 10 to the minus 14. And thanks to the great research work of our experimenters, they found here quantum memory architectures marked by the shaded areas, which are likely to render the predicted effects as observable at this sweet spot in a terrestrial scenario, which both fulfills this required 1 second storage time with optical clock transition memories capable to store, or already shown to be able to store photonic information coherently up to 20 seconds, while even maintaining the very sophisticated temporal resolution requirements in the high frequency separation regime, because in this regime the interferogram gets really noisy. So this makes me come to a conclusion. Yeah, basically we revised this Marzena and Hom experiments from the perspective of entanglement analysis, related it to entanglement monogamy, quantum enhanced phase estimation, Noon states, and a very important result is that some mutual entanglement correlations are sensitive where others are resilient against these gravitational effects, and that this can be probed in a drop tower terrestrial experiment. And this was basically everything, so I thank you for your attention. Yeah.